thank you all for coming out this evening. I'm really excited to introduce Dr. Kevin Miller to you all. So Dr. Miller is a professor in the Department of Psychology, the Combined Program in Education and Psychology, and the Center for Chinese Studies, all here at the University of Michigan. He received an undergraduate degree from Haverford College in psychology. He then went on to get a PhD in child psychology and school psychology at the same time at the University of Minnesota. Since then, he was a faculty member at Michigan State, the University of Texas, and the University of Illinois before coming here to the University of Michigan in 2005. Right? Dr. Miller examines the processes of thinking that occur as we learn something new. To this end, he has conducted extensive cross-cultural research in China and the US in areas of cognition, math, and literacy development. He is a fellow of the Association for Psychological Science, the American Psychological Association, and the Psychonomic Society. And he received a Research Scientist Development Award from the National Institute of Mental Health. He's also received many grants to conduct his research, including funding from the National Science Foundation, the Spencer Foundation, the Institute of Educational Sciences, and the National Institutes of Health. Dr. Miller's talk is titled, "Why Math is Hard for So Many Americans and What Parents Can Do About It." Here is Dr. Miller.
Well, thanks everyone for spending some of the daylight that you're saving here. It looks really nice outside, so I appreciate that you came down to the basement of the library here. I want to begin by acknowledging the context. And you'll see, I hope, that this fits in well with this talk that's about building on the past without forgetting it. You can see that in this library. I walked by the secret lab as I came in, and I'm very curious about that. But I'm pretty sure that wasn't what it was when this building was first opened. The symbols we use, which is going to be a focus of today, which have a real history to them that's important to understand because it plays a role in some of the difficulties that children have in acquiring mathematics, and obviously the land that we stand on. Now, the University of Michigan, where Pithy, Chris, and I, and maybe some others work, is built on land that was granted in a treaty in 1817 with an aim towards making it possible to educate some of the children in this area. And that's something that we have not particularly paid attention to, but I'm really happy to see increasing emphasis on that. Now, this analogy is not a perfect one because unlike symbols, the Anishinaabe and the other tribes are ongoing, vibrant people whose culture has changed and continues to evolve over time. But I think in each area, knowing the past can be a meaningful guide to the future. Now, I've taken out almost all the interactive parts of this as I added more and more stuff to it. I left one from what Rebecca said. Tell you what, let's do this. Why don't you think about this question, and we'll hopefully have some time to talk about it at the end. And you can think about, so take a moment to think about your ideas. Why do you think math is hard for many Americans? Because I can assure you that it is. And think about what your ideas are and whether they change at all in the course of this discussion. And either way, I'll be interested in hearing from you. So here's what I want to do today. I want to present some evidence that things have changed in Americans' mathematical ability, and mostly not for the better. And then I'll go through and talk about some work that primarily that we and others have done about how children learn about number. That's a mixture of cultural features, including the language and symbols that cultures present children, and the ideas and activity that children generate on their own. Then I'm going to talk a bit about beliefs and classroom practices. And I'm going to throw in an aside on literacy because I'm cognizant of the fact that we are in a library after all. So some of the things that I'm talking about related to mathematics I think are relevant to literacy as well. So I'll make that point. And then finally, I want to end by talking about, well, what can you do about this? And I'm thinking of people here being related to children or even for yourself if you want to repair limitations in your mathematical learning or learn new things. So a couple of notes of changes over time. Leikio Hatano had this argument that when a country has a national sport as part of its culture, that is, contests that almost all members find interesting to participate in or watch, the team representing that country tends to be strong, even if its population is small. I think that school mathematics is a national, in the sense used above, intellectual pursuit in Asian countries, here primarily East Asian countries, but not in the United States. Whereas students cannot escape from it in the former, in the latter they are told, at least implicitly, that if they are poor at or dislike mathematics, they're free to seek achievement in other areas. Another thing is a really wonderful book by Patricia Klein-Cohen called The Calculating People that adds a historical perspective about this. And one of the things that's interesting is that a lot of the sort of vaguely racist sounding things you hear people say about people from East Asia and mathematics, well, somehow it comes to them naturally, but you still occasionally hear that, were things that people once said about, Europeans said about Americans. And so we are a traveling and a calculating people, said Ohio booster James Hall in his book Statistics of the West, with evident satisfaction. Arithmetic, I presume, comes by instinct among this guessing, reckoning, expecting, and calculating people, said English traveler Thomas Hamilton, with evident distaste. Each man attached a different value to the idea, but both agreed that Americans in the 1830s had some sort of innate reckoning skill that set them apart from Europeans. Now, that's a long time ago, and everybody involved is long since dead, but I'm a developmental psychologist, and one of my favorite favorite cross-sectional studies looking at differences over time was one that Dave Geary and his colleagues published back in 1996. And what they did is they looked at current college students at the University of Missouri in Columbia, I think it is, and East China Normal University in Shanghai, and then older adults. And within each age group, they matched people for health. Obviously, the young people were healthy, the older ones not so much. They were all either current college students or college graduates, and they gave them a bunch of standard arithmetic and cognitive tests that are often used in longitudinal research. So they would say, give you a bunch of calculation problems and see how many you could do correctly in 2 minutes. So it would be like this. Addition problems like 19 plus 18 plus 27, and look, as I said, how many you solve correctly in 2 minutes. Now, if you look at the Chinese data, which are in red, you kind of see what you would expect. Younger people, are used to doing speeded tasks, and they do noticeably better than the older adults. But for the American sample, it's the opposite, which is kind of deeply weird. Being in closer to the older cohort and teaching people in the younger cohort, there really aren't too many cognitive tasks, speeded cognitive tasks, where older people do better than younger people, but this is one. Do you have a question? Oh, anyway. Yeah, Jen.
Yeah, by older, are we talking like seniors in high school or?
No, 70-year-olds on average. Yeah, I'm glad you asked that. So I was looking at current college students and people whose college days were 30 years ago. So there was some variation, but on average, 70-year-olds. Thanks for asking that. By the way, what is 19 plus 8 plus 27? Good. My guess is that some people calculated that automatically and some people didn't. And that's part of the story that we're going to talk about. Now, they also had mixed addition and subtraction. One of the things you find with age, the frontal lobe is sort of the first to go. So tasks where switching tasks is something that's harder for older people, and I can attest to that. And so for that, you see for the American sample, there is a drop with age, but a pretty shallow one compared to what you see for the in the Chinese sample. They did a task, you had to look at numerical strings and decide if they're the same or not. Like in this case, they're not. And you can see that it's parallel. So it's not just that there's something about students at the University of Missouri that, and similarly, they did a mental rotation task. This is a task, you see two figures like this, and you imagine if they're actually 3D blocks, could you rotate them so that they were the same? In this case, the answer is yes. And again, people get slower at that as they get older. Even architects who tend to be really good at it, but older architects are slower at that than younger architects. So differences that we're going to talk about are pretty large, they're pretty specific, and they're probably recent in origin. And this will lead me then to talk about how children learn about math, and we'll get back to some of these other questions in a bit. All right, when children learn to count, they need to learn a system of number names as they count, and that's not a trivial task. Here's a Baby Blue's cartoon. I don't know if you can read it, but the little girl says, Daddy, look, I wrote a 17. And she actually wrote 71. And the father says, no, sweetheart, that says 71. 17 has the 1 before the 7. So she flips it around, shows her mother this upside down 71, and says, Mommy, look, Daddy taught me how to make a 17. Maybe I should help you with your numbers from now on. Now, it's interesting, as you're about to see, that that's the example they picked, because that actually is a problem for English-speaking children. So let's look at number language and number naming in a couple of languages that I picked. So Chinese, written and spoken, and English and Spanish. What all these things have in common is that it's an unpredictable list. If you knew 1, 2, 3, 4 perfectly, there's no way in the world that you would guess as 5 is what comes next. Same with Chinese, if you can count 1, 2, 3, 4, wu would escape you. You can see for 1, 2, and 3, in written Chinese, there's a reason that the symbols are what they are, but that doesn't really get you very far. So from this point of view, learning to count to 10 should be equally difficult in each of these languages. Then there's the teens, the second decade, excuse me. Now, Chinese has a clear base 10 structure. So 11 corresponds to 10-1, 10-2, 10-3, and you can figure it out from there. 19 is 10-9, shijiao, and 20 is 2-10. Well, what about English? Well, there's 11 and 12. Apparently that sort of comes from like 1 left over beyond 10 and 2 left over beyond 10. But learning it so far, there's no clue that you're dealing with the base 10 system, because you aren't. Then 13 starts to have a structure, but it's the structure that English shares with other West Germanic languages, where you have the unit before the base. But English only does it from 13 to 19. You can still hear, 4 and 20 blackbirds and things like that, and looking that up some more for the talk, that apparently changed, the structure changed as late as the 1700s is when it became predominant, that we would say 24 rather than 4 and 20, but that's not what we do in the teens. Now, from my point of view, Spanish is even worse in the sense that you have a structure like 11, 12, 13, up through 15, like quince, but then you have 16, so 10 and 6. You have a nice regular structure, but it kind of randomly shows up in the middle of the teens decade. So you don't even have integrity for decades there. Other Romance languages do that. They don't all do it in the same place, which is weird, and I don't know why. One weird historical point, though, in English, teenager is a category. To me, 13 is a little young to say somebody's an adolescent, speaking from a perspective of parent and now grandparent, but that's where the number names change. Similarly, in Mexican and in some other Latin American societies, there's a big party when young girls turn 15, which again seems a little young to me, but instead of calling it a quinceañera, I guess it would be, sorry, my Spanish pronunciation is terrible. It would be something like what? Dieciséisera, which does not come trippingly off the tongue. So the ways in which these kind of entirely random structures of number names do have some consequences. But anyway, we're talking about learning to, to count. And the relevant point is that if you can count to 10 in Chinese, you use exactly the same structure in the second decade. If you can count to 10 in English, well, you don't really have much of an advantage. Now, from 20 to 99, these languages converge on a common structure. German and some other Germanic languages continue to do the 4 and 20 structure of the teens, but in English and Chinese, it's so 37, 37, qi is 3, 10, 7. In English, it's thir, like 3, t for 10, and 7, and similarly in Spanish. But the most relevant point is Chinese has been doing this all along, but it's an innovation for children when they're learning to count in English or Spanish. Of course, it's even worse for some other languages, particularly French, where to do not basically 92 is 420 plus 12 to form the name for that, which has got to be tough. Now, I will say that larger number names in Chinese get to be more complicated. Chinese has a base at 10,000. So the population of Ann Arbor would be something like, 10 or 12 10,000s. And so bigger numbers do get complicated. Chinese also will put a 0 in. So instead of, say, 1,005, it would be 1,000, 0, and 5 to represent the empty spaces. Okay, you didn't come here to hear about linguistics. Let's talk about children. Now, learning difficulties for children reflect the structure of language. So we had some 2.5 to 3.5-year-olds. We came back every month and had them just count as high as they could. And you can see that there's no advantage for the Chinese speakers. Learning to count to 10 is really hard if you're that small. It's a lot to remember. There's no order for it. If you look at individual children, they're just all over the place. One month they can count to 10, another month they can count to 3, and so on. But it's a hard thing to learn. But if you look at the 3-year-old group, the American kids, who are again in blue, are making the same slow, steady progress. But the Chinese kids, once they can count to about 20, really take off. And similarly, there's a point between the sort of 3.5 to 4.5-year-olds where kids sort of suddenly get it. This, by the way, is a very efficient way to do a longitudinal study. So across 1 year, we could look at different groups of kids, and you always have to worry whether being in this experiment, having somebody show up and have you do math has some effect. But you can see mostly it didn't. The curves line up pretty well. But we didn't have to wait 3 years to collect all the data. Another way of looking at these data is a survival analysis. And metaphorically speaking, let me say. So if you look at children's count, so we threw them all in a pot. So they're different ages of kids, but the two countries were the same, had the same distribution. You can look at where mistakes show up. And you can see lots of kids had trouble counting to 10. Naturally, those are our youngest kids, but it's not a difference between the two languages. Counting from 10 to 20 was hard for the little Chinese children, but it's dramatically harder for the English-speaking kids because they had more to learn. And then beyond that, kids would make mistakes at decade boundaries. In both countries, it was pretty common to go the equivalent of 27, 28, 29, 20. Now, the effects were pretty specific. I'm going to talk about this quickly, but this was a task where we had children produce sets of numbers of sets of 4 or sets of 12. And you can see there wasn't any difference favoring the Chinese children. So understanding the basic ideas about number and amounts, there wasn't any difference there. Okay, so what happens later? Now later on, Arabic numerals become the fundamental representation of number. That's somewhat easier to learn if you start from Chinese. Now, as a cognitive psychologist, developmental psychologist, it's kind of interesting that numerals become the, you have this new representation that becomes the underlying one. And I've had several experiences with speakers of Romance languages. Like, I have a friend whose husband is Italian, an Italian friend whose husband is American who's learning Italian, and at one point told her, well, I can never remember where the numbers switch. And his response was, well, I don't know what you're talking about. And similarly, I've talked to teachers who haven't been aware of the fact that English number names are backward. It's a good thing to forget, right? Because it's not useful to you unless you're going to be a preschool teacher or an early elementary school teacher. And Arabic numerals become the basic underlying structure of numbers. And so I would argue, there's some who disagree with me, but I would argue that the later differences that we're going to talk about don't have that much to do with these linguistic things that I've been talking about. But if you're around, someone, in the age of, say, 2 to 5 or 6, these are things that, matter to them and affect the difficulty of what they're learning. There's one of my favorite quotes from Wittgenstein that fits this as has many other things. There's the philosopher. Our language can be seen as an ancient city, a maze of little streets and squares of old and new houses, and of houses with additions from various periods. And this surrounded by a multitude of new boroughs with straight, regular streets and uniform houses. In many aspects of language, what's early and ancient is just sort of unstructured and irregular, but then, once people realize, hey, we have a city here, or we have numbers that are going to go on forever, then it becomes more regular as time goes on. Now, I mentioned that Arabic numerals are important. And some of this you can see going back, 1,200 years ago, or 800 years ago, to when they were first introduced to Europe. Leonardo of Pisa, better known as Fibonacci, argued that, but all this, the algorithm and the arch of Pythagoras, are regarded as an error as compared to the methods of the Indians. The 9 numerals of the Indians are these: 9, 8, 7, 6, 5, 4, 3, 2, 1. With them and with this sign 0, which in Arabic is called sephirim, from which we get cipher, any desired number can be written. And since you're also familiar with them, it's really hard to understand how big a deal that was. There was a period of time when if you were in England and you wanted to, say, learn how to multiply the way you all learned in, say, 3rd or 4th grade, what you would do is travel to Italy and you'd learn calculus. And the first step of that was you'd learn Arabic numerals, and then they could teach you how to multiply and divide. Now, learning this involves some transfer from the number naming system that came before, and some English-Chinese differences should carry over. Now, we can find effects in adults. I'll give you, Chris, would you like to be a guinea pig?
Sure.
Good. All right, so I'm going to see, you'll see a number like 37, and your task is to reverse it, all 2-digit, and say 73 as fast as you can. Hopefully it's big enough for you to read.
Okay, so
Yeah, go ahead. Yeah.
okay. So I see. Okay, so 27.
So you say 72. Yeah.
Okay, so 18. Oh, wait,
Yeah.
Sorry.
Okay.
So 61, 45. This is top 27, 58, 21, 83, and 60.
Good. So adults can do this. It's obviously not something you're automatic at, but for English speakers, places where you cross the boundary between teens and larger 2-digit numbers are slower, although interestingly, going from, say, 61 to 16, there's some priming from the positive names. So if you use numerals, which we did, and that's a little faster. All right, some conclusions so far. Early mathematical development is a mixture of language-dependent and universal factors. Sensitivity to the structure of symbols begins really early, as you can see from the studies with preschoolers. Base 10 concepts and teens are problematic for speakers of English, even though they become a part of the foundation for later mathematics. So English-speaking children face some disadvantages in learning about numbers, and similarly Spanish-speaking children in other European languages. We didn't really talk about this yet. Middle-class children have experiences that generally provide them with a basic understanding of numerosity. Not all children have these experiences, but we'll talk about some ways that can be provided. In some ways, I think about this as if there's a hole in the sidewalk. Most people aren't going to trip on it. I mean, I probably would, but you probably wouldn't. But if somebody trips, that's most likely where they're going to trip. And this is the way that I think about this. Most children make this transition from number names to Arabic numerals, and they forget and throw away the latter, and they don't have a problem, but some people do. So now I want to move on to talk about some beliefs and how this connects to practice, particularly classroom practices. But first, a couple of points about why you should care about this. One of my favorite books, it's really well written, Robert Moses, involved, well, more than involved, a leader in the civil rights struggle in the 60s in Mississippi, and then later became convinced that algebra was the real civil rights that was keeping a lot of black children from the lives that they should have, and came up with the thing called the Algebra Project. It's been a very effective sort of scalable way to teach kids algebra who might not otherwise learn it. A confident understanding of math opens some really important doors, careers, fundamental ideas, but I think there are multiple bad ideas and practices that keep us from achieving this, and this is what I want to talk about. But I mentioned a quick aside on literacy, because I know we're in a library. Even if you don't care about math, I think you should care about the processes and phenomena that I'm talking about here. American society is biased toward literacy over math. Its people will very freely admit that they're bad at math. They won't that they're bad at reading. Michael McCloskey at Johns Hopkins done some really interesting studies, because there are students at Johns Hopkins, so I'm sure there's students at Michigan who basically can't read, who are smart enough to make it to college. And these are just amazing people. They always go to class, they tape things, they study really hard, they do whatever they can to compensate for the fact that somehow along the way they either teaching or for whatever, they're not a good reader. But that's too shameful to admit. Where people are happy to say, you know, I'm just not a math person, I'm not good at math. In the same way that despite my grandson's best efforts, I'm really terrible at drawing. And I wish it were otherwise, and he is trying to change that, and I'm working with him, but it's something I'm willing to admit to you here. But there's some evidence that similar processes are going on with reading as well. So is this happening with literacy? There's some pretty good evidence that many people are reading less. Here, this isn't the best graph, but this is from the National Assessment of Educational Progress. And they have one version of it that tries to ensure comparability for tests over time. But you can see for the 10 years between 2012 and 23, the percent of students, these are, I think, 4th and 8th grade students, and 12th grades. Sorry, I think 4th, 8th, and 12th graders who say they read almost every day went from 27% down to 14%, so basically halved. They want to say one or more times a week. So those two together was 53% in 2012, down to 36% in 2023. And the number of people who say they never or hardly ever read went from 22% up to 31%. There are alternative ways to get knowledge and entertainment. And there's also evidence from eye tracking studies that kids aren't as advanced as they used to be in their reading. I'm not sure how big a problem it is, but it's certainly a big phenomenon. And in some ways, it echoes what's been going on in mathematical development. So now back to math. I believe that in the United States, there are a number of factors that conspire to convince students that math is something they can't understand, that it requires massive memorization, and only some people can do it. And I think that's the confluence of a number of cultural beliefs and practices that I'm going to talk about now. First of all, so let me lay these out and then I'll go through and talk about the idea that some people are bad at math. Mindset and some of its dangers that I want to talk about, maybe to be slightly controversial. A couple of things that have come from psychology, but psychology from long ago. You know, behavioral objectives, the idea that what's important is to be able to get an answer however you get it, versus the idea that knowledge is fundamentally a matter of relationships, and the idea that mathematical knowledge is a bunch of isolated facts and skills. Okay, let me start by talking about beliefs about learning. Lee Ross, back in 1977, identified something called the fundamental attribution error. And the basic paradigm goes like this. You record someone giving a speech saying that, you know, all the little kittens in the world should be killed. And then I show it to you and I and obviously most people don't agree with that, but the question is, how terrible is that person? Most people say pretty terrible. But I either tell you or I don't, that he was in a class and everybody pulled an assignment out of a hat, and his assignment was to do the best he could to convince people to euthanize cats, or you don't provide that context. For Americans and Europeans, that doesn't really matter. You're a cat killer and I hate you. And so it's called the fundamental attribution error because it's an error. Because generally people, particularly college students, will do that. You know, they'll do the assignment that's given to them. It has to do with attribution. Excuse me. Did you do it because you're a horrible person or because that was your assignment? And it's fundamental because they found it in many, many places. But one place where they didn't find that were in East Asian societies like Korea, China, and Japan. And there people say, well, you're a student. This is your task. You did it. Who knows what you really think? Americans tend to think that what you do reflects your kind of fundamental being, and vice versa. So if you're bad at math, it's because you're a bad math person. Some of this goes back to Calvinism, you know, the idea that God decided whether you're going to heaven or the other direction, and there's nothing you can do about it, and all I can do by interacting with you is get a kind of glimmer of which way things are going for you. Americans are more likely to believe that your intelligence is fixed, you are what you are, and that success is due to your ability rather than your effort. I kind of feel like we all know that's not true, but none, you know, that we all have the experience, certainly children do, of I couldn't do this yesterday and now I can. Or that if I try hard enough, I can do it. Now, this can be maladaptive. Right? Once you decide you're bad at math, it's really hard to convince you otherwise because most of your experiences are going to reinforce that. Teaching and assessment practices can also reinforce this idea. That one thing that I've observed in a lot of classes in the United States is a teacher will ask a question, somebody will know the answer, they'll give it, and the teacher will sort of believe, oh, okay, well now everybody understands it because they've listened to it being said. And to me it sounds like, you know, imagine I'm in a class and you're all speaking Italian and I don't know it. Questions are being asked, questions are being answered, but there's no way for me to get from where I am to where you are. Now, the more common practice in Chinese classes in elementary school is that probably I'll ask somebody who doesn't know the answer to the question first, but eventually I'll say, come to Macy, who certainly will know the answer, but then I'll keep asking other people. So it makes a lot of sense for Alice to listen to Macy, and because she can learn the answer and she can produce the answer, and there's actually some progress being made. Another idea that I think is mostly a positive one, Carol Dweck has talked about people who have different kinds of mindsets. And again, one I alluded to, the idea that your ability is fixed, God gave it to you, there's nothing you can do about it, versus the idea that if you expose yourself to difficult questions and problems, that you can actually become smarter over time. Now, mindsets are really important. There's a great quote from Henry Ford that whether you think that you can or you can't, you're usually right. And I think there's a lot to be said for that. My only concern with it and how I've seen it used is that mindsets aren't enough, right? That they affect how you spend your time, what you're thinking about, and whether you persist and so on. But the idea that just changing your mind is going to lead to some positive outcome doesn't work. Now, the last two things I want to talk about in the context of a study that we did, last two things in this part, where we asked US and elementary school teachers what's important about learning mathematics. The American teachers tend to focus on practice and repetition, whereas the Chinese teachers were focused much more on understanding, interest, the relationship between the child and the teacher. So here's some quotes, examples. The US teacher said, I think that drill is very important. I think that there's just no substitute for going over it and over it and over it until it's very firmly entrenched in their minds. With some students, these are different teachers, there can be something said for a lot of rote practice at the very beginning of a concept. There's some students who need 40 problems of it just to get the pattern of what they're doing. Chinese teachers, on the other hand, were more likely to just say things like this. What's most important is interest. The most important of all is interest. Besides interest, a solid foundation is also very important. Math is a system of knowledge, including many connections between the old and the new. Former knowledge will affect new understandings and consequently affect learners' interest. So we think a solid foundation is very important. And those ideas really fit what a lot of educational and developmental psychologists would say. So Mike Csikszentmihalyi done some really interesting work on people who become really good, say, musicians or chess players or so on at an early age. And it's interesting to think, how does anyone ever learn to play the violin? It's certainly not intrinsically rewarding, right? When you play it, it hurts your fingers, it sounds terrible, your siblings make fun of you, your parents run away, so it's really bad. And yet some people get over it, and what seems to be really important is the relationship they have with their first teacher. If you really love your first teacher, then you'll persist. And she thinks that you can learn this, then you'll persist to the point where, you can do it, and it starts to get interesting. My colleague Deborah Ball and her collaborators have argued kind of more systematically that mathematics is learned in relationships. So all these interpersonal relationships between teachers and students and among students and the environments they're in, but also the relationship with the content that they're learning. And understanding these connections are really vital to building and understanding an elementary school that you can move on from. Years ago, as part of a National Research Council report, in fact, where I first met Deborah Ball and a lot of people are now my colleagues, called Adding It Up, which you can download. But we talked about how mathematics was really, you should think about it as a rope woven with a number of different components. So adaptive reasoning, strategic competence, conceptual understanding, productive disposition, and procedural fluency. So all those things really need to fit together. Now, how this plays out in the classroom, if you see math as separate skills, as some of the American teachers talk about, you say, okay, now we're doing this, and you'll practice it 40 times until you got it, and now you do something else. So a lot of the speeded practice that American students do is stuff where they don't really have to think about it. You figure out the pattern, and then you just go through and write it down. If you see math as a network of concepts and calculations, though, you want to practice it in contexts that challenge the learner to think about what they're doing. So 2 quick examples. Reusser, the Swiss psychologist, has this amazing example. So there are 120 sheep and 5 dogs in a flock. How old is the shepherd? Anybody? Now what's amazing is, so my 9-year-old grandson is a really wonderful mathematician, but he can solve this problem, and he's not unusual. Because what you learn is, well, they're numbers, you put them together. Okay, can't be 600 years old. 115, yeah, not really, or 125. So, well, if you divide by 120 by 5, that'll give you a plausible answer, so that must be what they're looking for. And if you go, and I suspect at that age, I would have done that too, because I would want to be done with homework as quickly as possible. And so some way of putting the numbers together to come up with something plausible should be the way to do that. It doesn't work that way in the real world, or at least it shouldn't. And so that's not a good thing to be learning or practicing. Unfortunately, I didn't have time to look up a better example, but so in Chinese classrooms, usually 1 day a week, they'll have 2 minutes where you do as many problems as you can do. And so there's a lot of valence. You have to raise your hand to show how many you got right, and kids are really competitive and excited. But what's interesting is there are problems where there's a big payoff in thinking about what you're doing, right? So for a second grader, you can say, what's 999 times 5? Now, you could go through and do that as written, but then your 2 minutes are going to be up. Or you can say, well, I can multiply 1,000 times 5 and then just subtract 5 and then move on. So you have to think about what you're doing, remember what you've done before, and be clever at the same time that you're trying to be quick. And that's a great example of what we meant by this rope, that what's important about mathematics is how all these different things fit together. Last thing I want to talk about, a lot of this, you'll see, is very critical about American education. If you invite me back, we can talk about literacy and reading instruction, and I can give a more balanced picture, but this is the focus for today. So one sort of surprising thing, and certainly was surprising to my Chinese colleagues when I've talked about this, is that there's a big difference in the kind and distribution of talk in American elementary school classes versus the ones that we looked at in Beijing. This was in, the US classes were in Champaign, Illinois, so another university community. So here, hopefully you can see that, but in the Chinese classrooms, the preponderance were sort of whole explanations, whereas in the American classrooms, by far, they were just sort of raw answers rather than explanation. So let me give you an example. This is 5 minutes of student talk in two classes, the one on the left in Illinois and the one on the right in Beijing. So yes, once, 3, 1, 3 times 9, 3, 3, 9 times 9, a repeating number, repeating digit. Subtract $13.33 off the $40. Yes, 7, 6, you get the idea. In the Chinese classroom, I think 4 divided by 5 is 4/5. Then if it's 8 divided by the result of the bracket should equal 4/5. It equals 8 divided by 10 equals 16 divided by 20. 30 divided by 6 equals 15 divided by 3. Also equals 10 divided by 2 and 6 divided by 1, 5 divided by 1, and so on. So much more of the work is being done by the students in the Chinese classroom than the American one. Here is just looking at everything connected to mathematics beyond just a bare number and it's just ranked from most to least. You know, the classes don't line up with each other, but you can see they don't overlap. The students are doing much more of the intellectual work in the math classes in Beijing than in the United States. Give me another example. This works better as a video, but because this is going out on the web, we couldn't do that. So this is calculating 7% of 15, so you said $15 times 0.07. Now, this is what we're going to do. The teacher said, when we multiply, we have to take into account the digits that we had to the right of our decimal. How many digits to the right of this decimal? The students in unison say 2. How many do we have to the right of this decimal? 2. So how many is that altogether? 4. 4. So in order to get our decimal in the correct place, we're going to start at the end of the number that we got. And you already know that the answer is what? $1. Okay, that's not right, the right answer, but so it must have been a different problem. All right, so we're going to move this 4 decimal places because there are 4 places to the right decimal place. So this is, student counts 1, 2, 3, 4. What am I going to put here? The decimal point. So what does this amount equal? $1.05. All right, what should I do with those to erase them, the extra zeros? And this I would say is fine, but what's missing is any explanation of what you're doing. It turns out to be really important. If we had more time, you know, I'm sure you all know this thing of, you know, to multiply 15.00 times 0.07, you ignore the decimal point and you count back those number of places. But how would you explain that to a 4th grader? When I try that in classes I teach, people are generally at a loss. And that's interesting because it's a really easy explanation. What you're doing when you're turning 15.00 into 1500 is you're multiplying it by 100, by 10 times 2, and same for the 0.07. So if you don't fix it, you're going to be off by 10,000, by 100 times 100. And so you fix it by dividing what you multiplied by before. You know, people understand that the equal sign is this balancing. And so there's a pretty simple explanation, but understanding that is important because it helps you understand why you don't do that if you're adding the numbers, and it gives you a basis to think about how this would work when you come to algebra and you're thinking about numbers more generally. So there's a US focus on doing one thing at a time that's problematic. It's kind of boring. But more importantly, it's a poor basis for applications or for further understanding. When I went to college, they advised, you know, they said, well, you all took a language in high school, but unless you got a fair ways with it, you might think about starting over with a new language, which was really good advice for me, I have to say. I kind of feel that for some Americans, it would be nice if they could start over with a new mathematics. But of course, you can't. My daughter went through the LMAC program, the Elementary Mathematics Teaching Certification Program, which is a wonderful program, by the way. but they would take a course that would essentially try to give people a conceptual understanding of the mathematics that they learned. And my daughter loved the course and really learned a lot from it. But people were often crying. It was just really hard. In a semester, you can't kind of rebuild 12 years of education. And as I mentioned, in China, there's a much more focus on integrating and understanding that then provides a better basis for using what you've learned and building on it. Okay, the last part I want to talk about what we can do as parents, grandparents, aunts, uncles, and so on. So first of all, modeling is key. Children are prone to copy what they see adults do. There are many contexts for mathematical talk. My colleague Pam Davis-Keene and a number of her students have looked at mathematical talk at home. For some reason, a lot of it goes on at breakfast, which surprised me. But math talk in the home of preschoolers is related to children's learning. Now, the picture's there to remind me of how much devices have made this more complicated. One way that I'm definitely going to sound like an old man is that one of the things that makes me sad when I go to restaurants now, it used to be that parents would go out with their children and the child would often be the most interesting thing around. Now it's more common for parents to be looking at their phones and the kids, maybe they have their own device, but more often they're sitting around bored trying to figure out how to get attention from their parents. That's got to be a bad thing. I don't have a solution for it though. Games are also very useful. They're really great opportunities to count, compare, etc. Bob Siegler's done some interesting work on this and suggests that kind of linear-like games, so chutes and ladders is sort of linear, work better than kind of circular games. Interestingly, there's some nice studies that this can work as remediation for children who enter school without a good number sense. And a good question to ask your early school entering child is how much more is 7 than 5? That having that sense of the sort of an base intuitive number line is something that's really helpful for the math that's taught in school. There are a lot of resources online. Sesame Street, of course, which has gotten better. One thing I like that my grandson really loved and learned a lot from are number blocks, which is a BBC program. So if you're not familiar with it, if you're around somebody, preschool, early elementary school age, take a look at it. It's pretty useful. Now, for all these things, if you can watch it with a child and discuss it with them, that always works a lot better. And the last new idea, Anna Ostrom has talked about something called the panacea trap. The idea that complex problems can be solved with a single solution. She's interested in ecological issues, but I think it applies here as well. But the idea that there's going to be one, if we just get our curriculum from Singapore, or if we just do this, if we just do reading first in the morning or whatever, that'll solve things, that's never going to work. Math isn't like that, and improving math isn't going to be like that. So improving math in the United States is not a quick or a simple task. Mathematical knowledge itself isn't a single or simple idea. And notice that problems in schooling compound because much of what teachers know about math when they teach is what they learned in school. So if they've gotten a great education, they have a step up, and if they haven't, then that's going to show up in a lot of problematic ways. But the good news is that there are really important contributions that every parent, grandparent, aunt, uncle, leave anyone out, older sibling, can make to the education of their own relatives. So let me stop there. I'm happy to stay and talk afterwards, or you can email me at this address. There'll be time for questions, or if you want to talk about what you think the problems with American education are and things I left out, you're welcome to do that. Okay. Jen has a question. So thank you all.
All right.
We talk about literacy. We know there's a science of reading.
Yeah.
Where's the science of math?
There's a lot of work on that. Some by the same people, but so Bob Siegler, for example, you can look at that book that we did. I think it's actually pretty good. The Adding It Up, it was called. It's going on 20 years old, but these things don't change. But there's been a lot of research on mathematical development. It hasn't been quite as contentious as literacy for some reason. So I think there's more of a consensus. So great question.
Okay, any more questions?
I have a question about a few decades ago. I think there was something called the new math.
Yeah.
And it seemed like that was pretty unsuccessful. I wonder if you can
Sure.
comment about that.
Yeah, and actually I was somebody who, in my elementary school, I took new math, it's taught by nuns. And so I have some thoughts about that. So, because we would do a lot of stuff with sets and logic, and it was kind of fun, and then we'd do numbers. There's no way as a first grader, and even a pretty smart one, I could have understood how they work together. Now, people like Bertrand Russell had said, well, the way you should think about, say, 2 is it's the set, a superset of all the things in the world that have 2 elements, right? And you could generate numbers like this. You could line up, you have a few of them to start with, and then you line up the elements of the sets, and if there's some left over, you put that one to the right, and if the world is kind to you, you're going to come up with the natural numbers. And mathematicians said that's great. And they were also trying to respond to a problem that people had in college, which is that there were students who could calculate pretty well, but they didn't have an understanding of what they were doing. So like mathematicians, and I know many, they said what we need to do is start from first principles and then logically develop numbers. And I think teachers didn't really understand what they were doing. I don't think kids could have understood what they're doing. There are conceptual ways of teaching numbers, but starting with logic in general and then trying to generalize that to numbers, I don't think was ever going to work. So it was an understandable idea. It didn't lead to the kinds of outcomes that people wanted, and I'm not surprised. So good question. Yeah. There are, I think, 2 people before you, but she'll bring the. Go ahead.
So, thank you. It was a very interesting talk. So I'm one of those mathematicians, and
Good.
I first had a question, and then after that, I have a comment and now a question.
Okay,
So
good.
the comment is, the description of the new math you gave reminded me of a difficult to get hold of textbook called Mathematics Made Difficult, where it's like an entire textbook that motivates logically how to get to adding 1 and 1 is 2. Anyway, that's a whole other thing. The question I had was, I found it very interesting that you found that there was essentially this wall that people or kids have a hard time getting past when the fundamental sort of object changes from sort of linguistic to, I guess, numeric. And having taught calculus, what I notice is that as you get from sort of individual variables to changing the fundamental object again, but much further on in like sort of like freshman, sophomore in college, there's again another change where the fundamental object is now a function and things like that. Is that like a repeat that's happening now as an adult, or what is some commentary on that?
So in most cases like this, I think the issue is the kind of underlying representation that students have. So for example, my grandson now is starting to learn about fractions, and they just teach it in terms of operations. You have 4 things, and you take 2 of them, and so on. The other important representation for fractions is points on a number line. And you really need both of those. And in some ways, the idea that a half is a number and it's here is really, really powerful compared to, well, you can divide 1 by 2, except you can't, so here's what you end up with. And the problem is, so my idea about behavioral objectives is the idea is that, well, let's find a way that kids can get the answer. And that may not set them up for understanding it in a way that leads them to understand it in a deeper way later on. And cases where you think you understand something can be the most difficult to go beyond, right? I'd have to think about that specific case. I think it's an interesting one. But I suspect the kind of univariate representations they have are sort of slick tricks that work there, but don't generalize. And that it should have been taught in a way that kind of opened things up for the generalization. I don't know if that makes any sense to you.
I'd be interested to talk more
Yeah.
with you about it afterwards.
Okay. And you had another comment, or?
Oh, no, it was
Oh,
the mathematics made difficult comment.
Yeah.
I was just going to respond to your question, which is, I'm one of Kevin's colleagues, so
Yes.
and just really wanted to
participate and see what was going on. The cultural historical shifts from zero as a concept in human history, or infinity, or negative number, all of those kinds of conceptual leaps culturally as a social historical are also repeated at the ontogenetic level. So those broader kind of generational things that have been difficult for man to like develop with respect to mathematics gets repeated in the kind of individual development for children, which is it's fascinating, right? So it's not surprising in calculus when they're trying to conceptualize infinity or what that might mean, that that was a huge leap for the mathematical community as well, historically.
Thank you. That's really interesting.
Yeah, I don't think it has to be that way, but it often is, and it's a really good place to look.
I'm sorry, I maybe just don't know what in Chinese, what are the measurements? Like systemic measurements, or do they have individual, like a a liter or like a
Yeah.
meter?
So there are a number of interesting things. So there's a traditional system, but so a li was a third of a mile, but now a gong li, so a public li, is a kilometer. So they use kilometers like the rational part of the world does instead of the imperial system. There are lots of interest. I could talk for a long time about this, but traditionally there was a 10-day calendar, and there were 3 of those in a month, and that still shows up in some things. Now they have a 7-day week, but the names of the week, except for Sunday, are day names, or numbers. So day 1, day 2, and the month names instead of January and so on are 1 month, 2 months, and 3 months. So numbers are more frequent in Chinese and used more generally in Chinese than they are in English. Other than that, I would say measurement is pretty similar. Yeah. Here's just bring it. Well, there are people online, I think.
Okay. So I guess my question was, there seems like there was a push maybe in the last couple of decades to contextualize, I think, elementary and high school math instruction in the context of like real world problems. Yeah. And I'm wondering if there's any research to support that promotes greater like curiosity or like a sense of pragmatism among students that makes them more motivated to learn.
So I think for some people it does. So in China, that's a big thing. I mean, all questions are about factories and stuff like that. And I don't know how kids respond to that. But there's a problem with it. When I was on the Adding It Up panel, we had some people come and talk to us about math textbooks and show us them. And a lot of what happens is a lot of math textbooks have a ton of reading and stories, and then just a little bit of mathematical context. And the idea is that that's how you make it interesting, because it's not interesting in and of itself, right? And I'd like to see more effort put into finding cool and interesting problems, which I think kids can and do appreciate, at least the ones that I talk to, and less about saying, okay, well, this is boring, so we've got to hide it with a bunch of text. Yeah. So lots of these things, it's not exactly right or wrong, but there are ways of doing it that promote, focusing on what's important, and there are ways of doing it that distract from that.
Thank you. Is there any study on gender as far as understanding math? My father was a mechanical engineer who tried to teach me math, probably when I was in kindergarten. I couldn't get it. My brother, who was 2 years younger, would yell the answer from the other room, and I would just glaze over. I majored in English. That was much better for me, so I, understand what this is all about. But is there anything that indicates that men are better than women?
So it's a complicated question. This is going to be a long answer because it's an important question. So first of all, for some family dynamics kinds of things, my best friend is a psychologist at UCLA. His dad and mine were both engineers at IBM. And one thing that we discovered is we wouldn't go to our parents for explanations about math or science because somehow our brain would just shut off. And you just have to figure it out on your own. And my dad had done some teaching, and it was perfectly good at explaining things, but somehow that didn't work. And that's pretty common. The second thing that happens within families really powerfully are that kids differentiate themselves from each other. So a really small difference may be enough for your brother to say, no, I'm going to be the math guy, and then usually it works the other way, that the older kid gets first pick, and then the younger kid says, well, I'm not like her, so I'm going to be the rebellious one, or the musician, or whatever niche she's left open. I also think, and I don't really have good research on this, that because kids do a lot of reading outside school, or at least used to, is that I think what's done in school kind of matters less. That you may learn it on your own, or you may not learn your own, but the practice that you have in reading within that classroom is really small compared to what you can have outside of it. I don't think anybody really does a lot of math outside of school. I mean, I love math, but I can't say I really did much of that. And so I think that that kids may be more dependent on what's taught in school for math than they are for literacy. Secondly, again, this is partly generalization, but a little bit of research, is that generally speaking, girls pay more attention in school. And so therefore, they're more bound to the quality of what's being taught because they're paying attention to it. Where, certainly for me as a student, I was off thinking my own thoughts. So what was being taught didn't necessarily matter so much. So I suspect that if math is taught in ways that you can see, I can't really build on this, which is so often the case. The kids are taught tricks for doing things without understanding it, and that's not really a basis to go on from. And so it would make sense that boys or girls will say, okay, well, this doesn't make sense, and to the extent that you're listening to that, maybe that's a bad thing. I mean, this is like rampant speculation, but it's complicated. But the other thing that's been interesting, actually the same colleague I mentioned is interested in these topics. A lot of people go to community college and have to do remedial either math or literacy. And this really sad thing that happens is they often end up taking high school courses until their time or money runs out and they never really get a college education. And what happens in math is they end up essentially redoing what they did in high school that they weren't successful in. So their idea that seems to be working pretty well is say, well, let's teach people statistics. Statistics are really important for lots of jobs, and it's kind of cool, and the math is all there, so it's a real context for thinking about things rather than saying, hey, now we're going to do trigonometry. So I would encourage everybody not to give up on themselves, that there are a lot of really cool ideas about mathematics, and particularly if you have children or grandchildren, learning something yourself can be a really powerful way of modeling for children what they need to do, as well as fun for yourself. So anyway, I'd be happy to talk about that more, but those are some fairly random ideas about your good question. Let's see what. Hi, Hui.
Yes, I have a comment in regards to what she asked. Is there a difference between capability between boys, girls? My answer or my comment just seems really simplistic. And to me, to say that boys are better than girls, that's very, very sexist. It's a cultural thing. Society does not encourage girls to go into math and science, and there are specific programs like in college to encourage girls. I don't think you talk very much about teaching ability. The teacher can know everything there is to know about math, right? As much as Einstein, but it's how you convey it. So I think, there are as many situations as there are teachers, and I've taken classes at Washington Community College, and I think the teachers there are great. They explain things to me that somebody at U of M might not. I'm serious, it's a lot of egos too, but so how math is taught makes the whole, 100% difference. I had a very, very bad pre-calculus teacher in high school. And one day I said, what's the relevance of this? Why am I learning this? And so I think if you make something relevant to the student, that makes a big difference.
Yeah. Thank you. I saw a study years ago that said when teachers spend a lot of time saying that something's relevant or important, what students say is, oh, this isn't going to be interesting to me. So that it can work both ways. Because a lot of mathematical ideas are just really cool. They're neat ideas you're not going to run across otherwise. And that's something that, focusing on, okay, this will be useful to you when you're working, some imagined job in the future loses, but that's important too.
I'm from Eastern Europe, and I've often been struck and confused by what I perceive, maybe you can correct me, the giant difference in standards in school between American schools and like Eastern European schools. Like American schools are maybe 3-4 years behind, and I'm always
Yeah.
it's strange to me, and I was wondering what's the reason for this, and also the other difference that I've always been curious about is there. It seems to me that in the U.S. there's a lot more of an attitude of sort of having an option, and like you're you should study what you're interested in, and if math happens to be not something you're interested in, you don't have to study it. Whereas I think again, correct me if I'm wrong, my understanding was in Eastern Europe it's a lot more like they're mandatory things that everybody has to study and everybody has to get through, and it's not about interest, it's about like this is what you do at school.
Yeah, well, choice isn't always a good thing, right? Because particularly young people don't necessarily make the best choices. My colleague here, Kai Cortina, was involved in research basically comparing students in East Germany and West Germany after the wall came on. And generally speaking, the East German students were advanced compared to the West German students, in part because it wasn't anything better to do. And doing well in school was more critical to your life in East Germany than it was in West Germany, where you had more freedom and choices. So that's true. I mean, what we learn is in a kind of ecology. One thing I would have talked about if we talked about reading is that learning to read Chinese characters is really hard, and getting to the point where you can read independently is later than it is for American kids. And so that makes math in some ways more appealing there than it is here, because you can figure it out on your own in a way that, whereas a lot of kids get to the point where they sort of take off on reading and can read on their own in a way that happens a good deal later in China. So it's complicated. I mean, people are making realistic choices, and having a lot of choices isn't necessarily a good thing. As you can see, look around. But what you find is, though, in some ways there's a bigger standard deviation, right? Here, American students have a lot of free time. You can devote that to learning an enormous amount, or you can just be on TikTok or something. And so that a problem with that, of course, is that individual differences get to be bigger, and so there's a lot less uniformity in in our society, which again you can see in lots of ways. Anyway, great question. I think
Any more questions?
Jen has another question.
Oh, yeah.
Fine with me. Why don't you wait for the mic, though, so it gets on the tape. It's coming.
One of the things that a lot of the teachers are talking about in my kids' classrooms right now is dealing with having some kids who are way behind, who really lost the virtual year, and a whole nother set of kids who accelerated during the virtual year. And I'm wondering, do you see that in the Chinese classrooms, and how do they handle it versus how we handle it?
Yeah, so they do lots of things to try to get people at the same level that are pretty positive. That having kids who are advanced teach kids who are less advanced in doing group projects. And that really helps in a lot of ways, I think. In part because the kids who are advanced, having been one of those, don't necessarily know as much as they think they do. And having to explain something can be really powerful. And having people more at a level makes life a lot easier for teachers, for explaining to students, and for students to understand. We Americans tend to believe that everybody's really different, and so the best class would be just you and Plato walking in the groves of Academe or something, and that's not true. That you can learn a lot from others, even people who don't understand what you do. Now let me talk about we haven't talked about Japanese math education, but it's really interesting. So first of all, they want to have big classes. And the reason for that is a lot of their teaching involves, they may spend the whole class on one problem and something pretty complicated where a lot of people will have wrong ideas. And they really want all the wrong ideas to come out, which is why you want to have a large sample size so that, so let's say you're adding fractions with different denominators. There'll be some people who say, well, you just add the top, you add the bottom, you're all done. And there'll be lots of different ideas that people have. But having somebody advocating for that mistake, and then they hash it out, and then you understand why this is wrong and this is right. And that's really powerful because even if you don't invent that idea today, maybe you will tomorrow. So understanding why this is wrong is pretty powerful. And there are ways that variation can be used positively. It's demanding for teachers because they really have to understand and be able to respond sort of on the spot to all these kind of wrong explanations. But in the right circumstances, it can be really pretty powerful. Now, if I were a teacher dealing with that, I know the issues are terrible, and even getting kids to come to school is problematic still. So it's not something I have a solution for. But we don't do a good job in general at dealing with individual differences, in part because I think on some level we think there's nothing you can do about it, that you're a slow kid and she's a fast kid, and there the twain shall meet.
I wanted to know which nation dedicates most time to mathematics? Chinese, Europe, or America?
So that's a good question. If Kyle Cortina were here, he could answer that on the top of his head. So it depends on what level of schooling you're talking about. So like in Japan, they have this really wonderful kind of relaxed way of teaching mathematics that mathematics educators love, I love. And then they get to middle school and it's just cramming to get the exam to go into Tokyo University or something, and it just sort of all falls apart. Something similar happens in China. There's a lot of attention early on to student thinking. I've been surprised at the college classes that I've gone to that basically it's just sort of lectures and students mostly are on their phones and not paying attention. Pre-pandemic, we would have students from Beijing Normal University come and visit here, and students from Michigan would go there. And the Chinese students would always comment on how much, how engaged the American students were and how much they paid attention in class, because that was very different than in Beijing Normal, which is a top university, and I would agree from my own observations. In lots of countries, South Korea is probably in some ways the worst example because there's so much academic pressure. The kids go to these hagwons, these after-school, cram schools after school, and often till like 10 o'clock at night. And a lot of the focus is on math, Oh, so another thing that's interesting is in the United States, being special is really good. If you're the best trombone player in the country, you can probably get into this university. In China and Korea and lots of places, everybody takes the same exam, and whoever gets the best score gets in, with some small exceptions. And so in the United States, if you have some time to study, paying attention to what you're best at might make the most sense, because maybe you'll be good enough that this is a special skill. But in China, paying attention to what you're worst at is where you're probably going to make the most progress if you have an hour to study. And so that, again, is something that sort of pushes towards uniformity.
Okay, any more questions?
Sure. Okay, thanks.
I was just thinking about your previous comment and just add another question about tracking. When I went to school, there were tracks, the smarter math students and the middle and the lesser math students. I don't think they do that anymore. I think there's a concern about people feeling bad. Is there a loss associated with that? It seems like it makes sense that you're going to keep your interest if you're in the high track and are doing well, rather than having an entire mixture where you're pitching to the middle of the abilities rather than helping the ones that need help and challenging the ones that need challenging.
So I have ambivalent feelings about that, because I really do think there are ways in which having to teach your peers and respond to the mistakes that they make is a really powerful way to learn. And of course, you miss that if all you're doing is selecting people who already know things. It kind of depends on what's being taught. Like I think the California advanced tracks, essentially they just teach you next year's math this year. So it's not really any better or conceptually any more interesting. It's just a year early. So I don't have a good answer to that, and I don't think that there's a clear answer from the research that I've seen as to whether one is always better than the other.
So I just wanted please to know the class control, the focus, no noise about it. Like any traditions that kind of, okay, American, public schools, everybody silent, like versus other countries.
Yeah. Actually, there's just an article in the New York Times, I guess in England, which tends to follow real trends, that there's a real push now for schools where nobody can talk or so on. The issue I see in American classrooms is that because we try to individualize things, people are often doing very different things. And that's problematic in lots of ways, right? If I'm sitting next to Jen and she's good in math and I'm not, if we're doing different things, I can't really profit from what she's doing. But if we're all doing the same stuff, it's easier for everybody, for me as a poor student copying Jen, for the teacher teaching the students and so on. But in American classrooms, they're often pretty chaotic because people are in their pods working on very different things. I mean, one thing I've noticed just as doing research in schools is in the United States, teachers are pretty free about letting you take students out of the classroom to do your study. In China, they'll say, well, okay, this class you can take people, the rest of the time forget about it. But there are lots of ways that I think American schools don't really think about basic aspects of cognitive psychology. So American classrooms tend to be really bright, lively places, sort of like this one with lots of distracting stuff all around. In Chinese classrooms, they have all that stuff, but it's in the back. So with the lessons going on, hopefully the most interesting thing to look at is the teacher and not, this chocolate gift box or, whatever's up there. But then you have a break, and kids make more noise than you can imagine, run around and shout and look at the stuff in the back. So they have a lot of frequent breaks. So if you're in first grade, you can say, okay, just have to hold it together for 20 minutes and then I'll get to go out and run around. Whereas American classrooms often, have long periods of time where you're just sitting there trying to pay attention and I don't know, nobody can really do that, and with lots of distractions around you.
Okay, so yesterday I was at the Washtenaw County Literacy Coalition launch, and the IPSI assistant superintendent who does curriculum told us at least 20 times about the value of AI for Black and brown students. Can you speak to the use of AI in our classrooms?
So in classrooms, I don't know. I have to say, for what I do, some teaching statistics and so on, I've been kind of impressed with the ability of systems to come up with good explanations. Now, this is not controversial, like many things. And so, one thing I did, I'm on sabbatical now, but a year ago I was teaching a course, and there was a take-home exam, and ChatGPT was out, so I was worried that some people would have it and some people wouldn't because the university didn't make it available. So I figured for the second exam, I'll give you an answer from ChatGPT, and you have to do better than that. But the problem was that ChatGPT did a pretty good job. In some ways, I was saved by the GEO strike. It was the only good thing that came out of that, that I ended up canceling the exam. But it's something we've got to figure out. You can see if the American approach is, well, you just have to get the right answer, then ChatGPT is horrible because it's going to give you the answer, and all you have to do is paste it in without understanding what it's doing. But on the other hand, it can give good explanations. Like, my friend also teaches statistics, and there's a question about why standard deviations or correlations could never be above 1, which is kind of an interesting, he didn't have a good explanation for it, but he said, well, let's see what ChatGPT said. And he came up with a great explanation and lots of good examples of this. So it's a good question. It's something that we're adapting to, and it's going to be complicated. Yeah.
So another question I had is, as someone who, I got my diagnosis for ADHD after I got my PhD, which is introduced a lot of rough, ride along the way, I guess. So I'm kind of curious if research has shown along the way that there is any fundamental shifts in the sort of baseline that you're talking about of motivation and like classroom environment for teaching math as it applies to people with some sort of neurodivergence?
So it's really complicated. I mean, the diagnosis of ADHD is a mess because there's no very objective way of doing it. Here's one of my favorite studies. It's not that powerful, and Chris may tell me I'm wrong, but so there is a genetic marker for ADHD. Basically, the longer you run you have of this, the more likely you are to be diagnosed. But what's interesting is that interacts in a strange way with the parenting that children get. So there's something called responsive parenting, the kind of middle-class parents that we probably all hope to be, that you ask your students lots of questions, you build on their ideas, those sorts of things. Students who had that marker and that kind of parenting actually did the best on the kinds of attentional tasks that they were looking at. Whereas if you didn't have that, then you were likely to be diagnosed as ADHD. So attention's complicated. Clearly, everybody I know, myself included, feels that their attention span has gotten worse. There's some data that suggests the opposite has happened, so it's complicated. So I don't have anything useful to say. I guess I should say, I'm going to stop there, but.
Okay, any more questions? All right.
Oh,
one more. Okay.
Good. Thank you.
Okay, this is just a general question in educating, which is, in order to, convey, like, say, to your child, whatever, my children are, ages 11 and 14 respectively,
Yeah.
and what kind of tone should be used, because, obviously it requires an awful lot of patience and
It does.
sometimes.
Yeah.
So what, based on your research, have you come with any theories on, like, what kind of tone to use with them?
Yeah. So here's my favorite innovation I've seen a teacher do. Something that she called my favorite no. So she would pass out difficult questions for kids to do, and then she'd pick out somebody who got the wrong answer, but in an interesting way. That you really want to focus on what they're thinking and not getting to the answer. And of course, in some ways, maybe that's the answer for ChatGPT, I'm not sure. But to the extent that you can show them, oh, this is an interesting problem, explain how you're thinking, let's see where you went wrong or why you did that or so on. I think that can be powerful, again, for some children. And, adolescents need to individuate themselves from their parents. So to some extent, in some cases, there may be nothing you can do. Maybe sending them over to a neighbor might be a better strategy. But I do think showing that you think this is interesting and that you think that their ideas about it are interesting can go some ways towards keeping them engaged.
Great. Okay. Thank you so much.
All right, well, thank you. Those are great questions, everyone. Okay.